From the intricate workings of a supercomputer to the seemingly simple smartphone in your pocket, an invisible engine tirelessly orchestrates every digital command. This engine, the microprocessor, underpins our modern world, yet its complex evolution often goes unnoticed. Industry analysts often refer to it as the brain of any electronic device, a testament to its profound impact since its inception. We trace its origins, the relentless innovation it spurred, and its potential future, revealing how a tiny piece of silicon transformed human capability. The genesis of this revolution can be traced to November 15, 1971, with the official release of the Intel 4004. Developed by Intel engineers Federico Fagin, Mark-Ian Horff, Stanley Mozor, and Masatoshi Shima, this single chip contained 2,300 transistors and could process 92,000 operations per second. Historical accounts suggest its initial purpose was for Busicom calculators, but its broader implications quickly became apparent. The Intel 4004 marked the definitive shift from bulky, multi-component circuits to integrated, programmable silicon, heralding the age of the microprocessor. The rapid advancement observed in the decades following the 4004's debut was famously encapsulated by Gordon Moore, co-founder of Intel. In 1965, Moore posited an observation, later termed Moore's law, stating that the number of transistors on integrated circuits would double approximately every 2 years. This wasn't a physical law but rather an industry forecast that became a self-fulfilling prophecy, driving relentless innovation. As tech historian George Gilder points out, it shifted focus from discrete components to integrated density, fundamentally altering design and manufacturing paradigms. As microprocessors became ubiquitous, fierce competition ignited. The CPU wars primarily saw Intel and AMD lock horns, largely competing within the x86 instruction set architecture. Intel, with its early market lead, established a dominant position, particularly in desktop and server markets. AMD, however, consistently pushed boundaries, often releasing competitive alternatives that challenged Intel's supremacy. This rivalry, particularly through the late 1990s and 2000s, according to technology journalist Robert X. Cringely, drove significant price-performance gains for consumers, fueling innovation on both sides of the divide. While Intel and AMD battled in the desktop arena, another architecture quietly began its ascendancy, ARM. Developed initially at Acorn Computers and later spun off as ARM Holdings, this reduced instruction set computer RISC architecture prioritized power efficiency over raw clock speed. Industry reports indicate ARM's design philosophy made it ideal for portable devices, including early PDAs and, crucially, smartphones. Its modular, licensed approach allowed numerous manufacturers to integrate ARM designs, democratizing access to processor technology and challenging the x86 hegemony in mobile computing. The journey from a digital design to a physical chip is an engineering marvel of unprecedented scale and precision. Modern processors demand features measured in nanometers, pushing the limits of physics. Manufacturing a single wafer involves hundreds of complex steps, executed within hyperclean environments, often termed cleanrooms, which are orders of magnitude cleaner than surgical operating theaters. As a spokesperson for TSMC once stated, every particle is an enemy. This meticulous process, involving billions of dollars in infrastructure, is crucial for producing the tiny, powerful chips we rely upon daily. At the heart of modern chip manufacturing lies photolithography, a process akin to photography but on an atomic scale. It uses light to transfer intricate patterns onto a silicon wafer, layer by tiny layer. A photosensitive material, called photoresist, is applied to the wafer. Then, an extreme ultraviolet or deep ultraviolet light beam projects a circuit pattern through a mask onto the photoresist. Areas exposed to light change solubility and are then etched away, sculpting the silicon. Chemical engineer Dr. Helen Lee explains, it's literally drawing with light, layer by precise layer, building a 3D structure. The quest for ever smaller features led to the development of extreme ultraviolet, or EUV, lithography. This technology, pioneered and dominated by the Dutch company ASML, utilizes light with a minuscule 13.5 nanometer wavelength, far shorter than previous methods. ASML's gargantuan EUV machines, each costing upwards of $200 million, are engineering marvels, employing molten tin droplets vaporized by high-powered lasers to generate EUV light. Without ASML's advancements, chipmakers like TSMC and Samsung would struggle to produce the leading-edge processors that define our current technological landscape. As Moore's law faces physical limits, the future of processing increasingly shifts towards specialization. Artificial intelligence, or AI, workloads demand massively parallel computations, driving the development of specialized AI chips. Graphics processing units, GPUs, from companies like NVIDIA, originally designed for rendering graphics, have found new life as AI accelerators due to their parallel architecture. Beyond GPUs, companies are now designing dedicated application-specific integrated circuits, ASICs, optimized for neural network inference and training, indicating a move away from general-purpose processing towards highly efficient, task-specific silicon solutions. Beyond conventional silicon, a more profound shift looms: quantum computing. While still largely theoretical and in early development, quantum processors aim to harness principles of quantum mechanics, such as superposition and entanglement, to solve problems intractable for classical computers. Instead of bits, they use qubits. However, challenges are immense, maintaining qubit coherence, requiring extreme cold and isolation, and mitigating errors. As physicist Michio Kaku suggests, quantum computing is not about making classical computers faster, but about fundamentally changing how we calculate. It represents a potential paradigm shift, though its widespread application remains a distant, yet intriguing, prospect.